Let's see another example. The question says that suppose you have two dice, pink and blue. If you roll them together, what is the probability of having at least one 6? Okay, so you're rolling two dice and expecting a 6 from any of them. If both of the dice roll 6, then that's also okay. So you are going to find the probability. So in this problem, we are going to try to solve this problem in different ways. Okay, so this is the fun part of solving probability problems, that if you have a good knowledge on the probability basic theories, then you can design your solution the way you like. So let's start. In the first way, we can calculate the probabilities of different cases and then finally add them to get our final result. So we can call it case-wise calculation. So what are the cases I'm talking about? Let's see them. So let's have a caption, pink here and blue here. So case 1 can be the pink die shows a 6, the blue doesn't. Okay, this can be a case, and this is an acceptable case because at least one 6 is found. Okay, case 2 will be the pink doesn't show a 6 but the blue does. Okay, that is case 2, just similar to the case 1. And case 3 is something I think you have already figured it out. That is, both of the dice show 6. Okay, so these are the three cases whose probability are things we are interested in. So now for case 1, we are going to calculate the probability of each of the cases separately. Okay, so for case 1, let's define an event C1, which is pink rolls 6 but blue doesn't. Okay, this is our event C1. So what might be the probability? So we see that there are two parts in event C1. The pink has to show 6 and the blue doesn't have to show a 6. Okay, so the result of the pink die is not dependent on the result of the blue die. Therefore both of these events, okay, are independent. Therefore we can say that probability of C1 equals to the probability of the pink die to show a 6, which is 1 by 6 trivially, and the probability of the blue die to not show a 6, that is something tricky. So the probability for the blue die to show a 6 would be 1 by 6. So the probability of this event to not happen would be 1 minus 1 by 6, right? That is something we have discussed before. So both of these events have to happen together to make this C1 happen. Therefore 1 by 6 times 1 minus 1 by 6 would be the probability of C1. Okay, this is simple. Therefore the result is 5 by 36. Okay, all right, so now comes case 2. Case 2, P of the C2 is pink doesn't roll 6 but sorry, okay, but blue does. Okay, so similarly P of C2, here blue is showing a 6, so the probability for blue to show a 6 would be 1 by 6 and pink to not show a 6 would be 1 minus 1 by 6. Okay, now the probability will be 5 by 36 for case 2. And our final case, case 3, it has C3, both show 6. Okay, now P of C3 equals to 1 by 6 for the pink die to show a 6 and 1 by 6 for blue die. So I'm sorry for the noise, would be 1 by 36. All right, now if we name our final event the expected event C, then C would be C1 union C2 union C3. Why so? Because union says that there is an or relation in between these events. Okay, so when we are relating C1, C2, C3 by union, we're saying that in my final event C, either this can happen or this can happen. Okay, so any of these events happening and we are good to go. All right, therefore C equals to C1 union C2 union C3 is the final event whose probability is something that we've been looking for. So P of C1 union C2 union C3 is something we're going to determine now. Before that, I have a question to you. That is, do you think there's any common outcome in between these two events, say C1 and C2? No, there's no common outcome, which means C1 and C2 are disjoint events. There's no common outcomes in between two events because let's say C1 has the outcomes where pink dyes show 6. The pink dye shows 6, okay, but C2 has all the outcomes where the pink dye doesn't show 6. So there cannot be any common element in between these two sets. Similarly, we can say that C2, C3, C1, C3 also are pairwise disjoint. That means C1, C2, C3, all these events are pairwise disjoint. So why have I come to this conclusion about this disjoint relation between these three sets or events? Because we are going to use our axiom 3 here, where we say that if A and B are two disjoint events, then probability of A union B would be probability of A plus probability of B. So here these are the three disjoint sets, so we can say that probability of C1 plus probability of C2 plus probability of C3 would give us the probability of C1 union C2 union C3. Now as we have determined the values of the cases, so we are going to put it here and finally calculate our desired probability, which is 11 by 36. So let's see if we can solve this problem in an easier way or not. Okay, let's go back up and try to solve this problem using something called principle of inclusion and exclusion. Okay, I'm pretty sure that you've heard of this term as you've studied it in your lecture on set, and we've also used it in our derivation of axiom 3. Okay, so the formula looked like this: P of A union B equals to P of A plus P of B minus P of A intersection B. Okay, so in our axiom 3 we see that the third term does not exist there. Okay, why so? Because in the condition of axiom 3 we say that if A and B are two disjoint events, then P of A union B would be the direct sum of P of A and P of B. Why? Because if A and B are disjoint sets or events, that means A and B have no common element. Therefore, A intersection B equals to null. So the number of elements in A intersection B would be null. Therefore, by the definition of probability, sorry, we would get that P of A intersection B equals to 0. So yeah, but there might be cases when we don't know whether A and B are disjoint events or not. In those cases, or in general, this is the formula to remember. Okay, so this is a very important formula when we don't know about the sets or events A and B, whether they're disjoint or not. Then we are going to use this general formula, so keep that in mind. We're going to use that in future. Okay, so this is the formula of principle of inclusion and exclusion. Now we're going to define our events A and B carefully. So let's say A is the event where the pink die roll 6. Okay, and B is the event of the blue die rolling a 6. There's a point that I want you to note carefully. That is, while defining event A, the only thing that I was considering is the result from the pink die. Okay, I have not mentioned any information about the blue die's result while defining A. Okay, there's only one part here in the definition of A, but during the case-wise calculation, while we were defining C1, we defined it like this, that pink die rolls 6 and blue die doesn't. So there were two parts in the definition of C1. So A and C1 are not the same event. All right. Similarly, B is the event where the only thing that I'm considering is the blue die's result. Okay. So now my next question to you is how the event of my interest in the question related to A and B. All right. How can I express the event of having at least one 6 with A and B? That is the question. So if I say that A union B is the desired event, would I be wrong? No, I wouldn't, because A union B means either the pink die or the blue die shows a 6. Now consider that if any of the dice shows a 6, that means we have got our expected 6. Okay, then both of the dice showing a 6 is also inside the event A union B. So A union B is the event that we were looking for. Therefore, P of A union B has to be determined. Okay, now we are going to use the formula. Before that, we are going to determine P of A and P of B and P of A intersection B. Okay, now P of A. What is P of A? P of A is a probability of rolling a 6 from one die, which is trivially 1 by 6. Similarly, for blue die to roll a 6, the probability would be 1 by 6 as well. Now, interestingly, what is P of A intersection B? Here you see that A and B are independent events, so their outcomes doesn't depend on the other. Therefore, we can say that P of A intersection B equals to P of A times P of B, where both of the values here are already found. So we can put 1 by 6, 1 by 6 here, and finally we get P of A intersection B equals to 1 by 36. Now, P of A union B, according to my formula, would be 1 by 6 as P of A, 1 by 6 as P of B, minus 1 by 36 as P of A intersection B. Okay, so finally the result would be 6 plus 6 minus 1, which is 11 by 36, exactly the same as the result from our last time. All right, so this is an easier way. So we still haven't seen the easiest way to solve this problem. Do you know that? Let's see. So in this way to solve this problem, we are going to use complement events. Let's go back up and start with our caption using complements. So let's say n is the event of my interest, where n is having at least 1 6, right? This is the event whose probability was expected. So what would be NC? NC is the opposite event to N, right? Therefore, NC would be the event of having no 6, okay? Right? N means having at least 1 6, and NC means having no 6. Now, we are not going to determine the probability of P of N directly. Rather, we would find the probability of NC, and then to find the value of P of N, we will subtract probability of NC from 1. All right? So we are going to search for P of NC now. Okay? So P of NC equals to what? NC is the event of having no 6 from both of the dice. Therefore, there are two parts contributing to this event. One is from the pink die and the other is from the blue die. Okay, so NC consists of smaller two events, which are having no 6 from pink die and having no 6 from the blue die. Both of these events are happening together to make NC happen. All right, therefore we can say that P of NC equals to the probability of having no 6 from blue die, which is 1 minus 1 by 6, we have seen it before, into having no 6 from the pink die, which is also 1 minus 1 by 6. Okay, so both of these independent events happening together making NC happen, and this is the probability of NC. So which becomes 5 by 6 times 5 by 6, which is 25 by 36. So this is the probability of my unexpected event. Now I'm gonna use the formula of complementary events. We've referred to the same formula in some of our previous examples. So 1 minus 25 by 36 becomes 36 minus 25 by 36, and here it is. Voila, 11 by 36. Exactly the same result, but with a much less effort. Okay, so let's add something before ending this segment. That is, do you know that there are ways where we can use the idea from our combinatorics lectures and solve this problem without directly using any of the basic theories of probability? Yeah, let's see a bonus way to solve the same problem again, and we will end this segment by doing it. Let's go to the next page. Yes, we're going to solve this problem using a combinatorial approach. Okay, so let's start with a caption which is using combinatorics. All right, so now the first thing that we're going to do is to find out the total number of outcomes while rolling two dice together. Okay, we already know that it's 6 times 6, which is 36, because we have seen it in some of our previous examples. If you don't remember it, then a quick review here. Suppose there are two boxes. The first box has to be filled up by the result from the pink die, and the second box will be filled up by the blue dice result. So there are 6 options for the first box, 1 2 3 4 5 6, and 6 options for the second box. Therefore, the total number of results will be 6 times 6, which is 36, and the results will look like this. Suppose we are putting the result from the pink die as a first element of an ordered pair, and the second element of the ordered pair will come from the result of blue die, then 1 1 1 2 1 3. So these are the outcomes. So there will be 6 and 6 at last. So there are there are 36 number of outcomes here in this set. So this is the sample space. All right, and the cardinality of the sample space is 36 here. Now we have to find out the number of outcomes where there's at least 1 6. Okay, so number of ordered pairs where at least there's 1 6. So for this calculation, we will not calculate it directly. We are going to find out in how many ordered pairs there's no 6 at all. That means in how many outcomes there's no 6. Just like the way of calculating our complement events, we're going to calculate in how many results there's no 6 from both of the dice, and then we will subtract the number from the total number of outcomes here. Okay, so let's see what we're talking about. So since there can be no 6 in any of the boxes, so now to fill up each of the boxes there are 5 options: 1 2 3 4 and 5. So 5 options for the first box, 5 options for the second. So the total number of outcomes where there's no 6 is 25. Okay, so 25 outcomes where both the dice roll no 6. All right, now we've already found the total number of results. Now you found the total number of outcomes where there's no 6. So if you subtract this 25 from 36, these 11 outcomes will have at least 1 6 in them, because the number of outcomes without any 6 have been subtracted from this 36. So these 11 outcomes will have at least 1 6. So to make you believe, I've already prepared a chart where these 11 outcomes are plotted, right? See this pink and blue. So this is the result. This column signifies the result from the pink die, and this is for the blue die. So 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, and then 6 5, 6 4, 6 3, 6 2, and 6 1. So if you start counting, you will see that there are only 11 outcomes here. So we are right. So this 11 is the cardinality of the expected event of mine. So it's cardinality E equals to 11. Say E is my expected event. Therefore, the final probability will be probability of E equals to 11 by 36. Again, we have found our desired result. I hope you understood it.